Welcome to this lecture about heat pumps for moderate and cold climates and the heat sources that can be used. In a previous lecture, we addressed other aspects of efficient HVAC systems in these climates. We will not address hot tap water, only space heating. From the 6 options we have to generate heat, we already dismissed a few of them as having too little potential for long-term sustainability. In this lecture, we will address mainly heat pumps and their combinations with solar and geothermal heat. And of course, you remember that to cover the peak load, in general, additional electrical or fuel boilers are used. They have a high peak power, but are functioning only a few hours a year, so they use very little energy. Heat pumps are one of the most important solutions. Heat pumps need low temperature heating and a heat source with as high as possible temperature, otherwise their efficiency is low. In cold countries, the use of outdoor air as source, as here, is therefore not a good solution, and ground source heat pumps will be preferred. The ground is always much warmer than outdoor air because of the continuous heat supply from the core of Earth. For a quick estimate of ground temperature, you can assume that it is constant over the year. At the average annual air temperature in the Netherlands, that would be around 9 degrees Celsius. So in cold countries, ground source heat pumps are generally preferred. Let's look first at the heat pump when the heating demand is moderate. You see here a PNID of a complete heat pump system connected to the rooms of the building. In the middle, the heat pump with its evaporator below and a condenser above. The compressor of the heat pump uses electricity. You see below a heat exchanger in the ground and above an electrical resistance and a boiler. Completely on the right, you see the rooms to which heat must be delivered. You also see on the top left an outdoor air heat exchanger, but we don't consider it yet. Only the lines that have a color are active, except for the heat exchangers line, which are always gray but are active when connected to colored lines. When there is a heat demand, heat is produced at the condenser side of the heat pump. You see it in red. The condensing refrigerant in the heat pump gives its heat to the water of the hydronic system, which delivers it to each room. Those are the red lines. In the radiators or flue heating of each room, the water is therefore cooled and goes back to the condenser. Look at the purple lines. In the condenser, it is heated again, and so on. The heat pump needs electricity to power the compressor, and it needs heat from the ground. There is water or water glycol circulating in the ground heat exchanger and taking heat from the ground, let's say at 9 degrees Celsius. The water at 9 degrees is transported to the evaporator, that's the dark blue line, where it gives heat to the refrigerant that is able to evaporate at such a low temperature. By giving its heat, the water is of course cooled down, maybe to 5 degrees Celsius, and is then transported back in light blue to the ground heat exchanger, where it is heated again, and so on. It may also be that the heat demand in the rooms is such that the heat pump alone cannot provide all needed heat. When this happens, has been decided during the design by analyzing the load duration curve. In that case, you see now that the warm water coming out of the condenser in red is directed to the electrical resistance of the boiler and is heated there further before being sent to the rooms. All other things are identical to the previous slide in mode 1. One problem that may be encountered is that during the cold season, the ground close to the ground heat exchanger becomes colder and colder because the warmth of Earth's core is just not enough to compensate for the heat being taken away. There are different ways of coping with that. In general, such a heat exchanger consists of many different vertical tubes. For this reason, they must be placed far enough from each other. If the heat pump is switched off during the hot season, the temperature in the ground will be regenerated naturally because of the warmth from the outdoor air, solar radiation, and heat transfer from the core of Earth. If the cold season is not too long and too cold, that works well. However, when the warm season is short or not that warm and sunny, it may be that the ground temperature at the end of the warm season is still too low, which will create problems in next winter. This also may happen if the heat pump is used in summer to provide hot tap water. In this case, an outdoor air heat exchanger can help adding more heat into the ground in summer. The warm outdoor air left above gives its heat to an additional water loop, which brings the heat to the ground heat exchanger, such the red line. The water is therefore cooled in the ground and pumped again to the air heat exchanger, such the purple line. Instead of using an air heat exchanger, it is also possible to use heat from solar collectors. A last possibility to regenerate the ground is offered when the heat pump is used as chiller during summer. Well-insulated houses may need some cooling, and the floor heating can then be used as floor cooling if the humidity is not too high. Some dew point control should then be added. Anyway, the cold produced at the evaporator site does not go to the ground anymore, but is now diverted through the hydronic system to the floor cooling in the room. See the light blue line. The hydronic water in the floor is heated by the warm room air and goes back to the evaporator, such the purple line, where it is cooled again. The ground heat exchanger is fully bypassed. At the other side of the heat pump, the condenser must reject heat. The warm water coming out of the hydronic system at the condenser side is led through the red line to the ground heat exchanger, where it heats the ground. The water cools down, of course, and is led back to the condenser through the orange line. In comparison with the first diagram that we had, new pipes have been added for the cooling, but we have now a possibility to cool the building. When it is needed, the regeneration by cooling can be combined with the regeneration with the air heat exchanger or the solar collector. Well, after these 6 different modes in which a ground source heat pump could work, let's look at a completely different system. Instead of using the ground, there are systems using the return air from ventilation as heat source. In this case, there is no direct heat recovery between supply and exhaust ventilation air. This is much better than using cold outdoor air, as indoor air can be expected to have a temperature around 20 degrees Celsius. In fact, that would even be better than a ground source heat pump COP-wise. There is only one little problem here, and that is that the volume flow rate of hygienic air is much too low to provide enough heat to the evaporator of the heat pump. So the return air will be mixed with outdoor air like that, in order to have the right flow rate. This decreases the temperature of the heat source and the COP. Such systems have in general a lower COP than a ground source heat pump, but a better one than pure outdoor air heat pumps. The figure shows only the working mode without peak load. If there is peak load, the boiler or electrical resistance would be switched on. These heat pumps are also called air-water heat pumps. At the evaporator, the source is air, and at the condenser, the sink is the hydronic system, water, therefore. Note that with air heat pumps, much care must be taken of freezing of the pipes at the evaporator side. It is very important to have a defrost mode and to insulate the pipes. This is the P&ID when the heat pump works in cooling mode. The ventilation air from outdoor is cooled in the evaporator of the heat pump, and the cooled air is distributed to the room. That's the light green lines. The warmer return air is just exhausted outdoor. See the dark green line on the left. And what happens in the hydronic system? Well, the water is diverted to an outdoor air heat exchanger where it heats outdoor air. See the red and purple lines above the condenser. This working mode is well known. Most split units and home air conditioners work like that. Solar heat can also be used as a source for heat pumps. The heat can be collected by a simple solar collector and stored in a buffer tank to be used as source for the heat pump. You see here in orange that the warm water from the upper part of the buffer tank is led to the evaporator, where it is cooled down and returns to the bottom of the buffer. At the other side of the buffer, the cold water circulates to the solar collector, where it is heated and returns to the upper part of the tank. Using a tank is unavoidable because of the intermittency of solar radiation. Even better is to use a PVT system. A PVT system is a photovoltaic system producing electricity, therefore, but also heat. The T in PVT is for thermal. The efficiency of PV cells is higher when they are cooled. There are therefore systems in which the PV cells are cooled down by water flowing on the back of the panel. So the PV cell acts as a solar collector, and for a part of the day, the PV cells also produce the electricity needed by the compressor. This is a very promising development. There are also many cases in which a collective heat source is used that operates a whole neighborhood. Collective heat sources may be, for instance, seawater if the location is close to the sea. Seawater at 10-meter depth is colder than the ground, but much warmer than outdoor air in winter. An example of such a system is the seawater plant of Duindorp in The Hague that worked for more than 10 years. A problem with seawater is corrosion, so special ducts and heat exchanger must be used. An advantage is that there is no need for regeneration. Sewage water could also be used from the main sewage duct or from the water treatment plant. When high-temperature geothermal heat is present, there is no need for heat pumps at all. But with shallow geothermal, collective heat sources can be designed as well. The working is similar to the one of individual ground source heat pumps we described extensively at the start of this lecture. In this lecture, we looked into more details to the design of heat pumps, as they are very important heat generators in HVAC systems. We described the working of 3 different types of heat pumps: the ground source heat pump, the ventilation return air heat pump, and the solar heat pump. For the ground source heat pump, we described 2 heating modes and 3 regeneration modes, including cooling. When it comes to air heat pumps, we looked at the use of return ventilation air as heat source, as in cold climates this is more efficient than simply using outdoor air. For solar heat pumps, we looked at solar collectors and PVT systems. And finally, we made a brief overview of collective heat pump sources. I hope you enjoyed this course. Thank you very much for your attention. Goodbye.